Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Hideki Yukawa's 1935 paper proposing a Meson theory of nuclear forces stands as a monumental achievement in 20th century physics. The work attempted to address a fundamental puzzle. Within the nucleus of the atom, what force could possibly overcome the immense electrostatic repulsion between positively charged protons, binding them together in a stable nucleus? Prior to Yukawa's insight, the prevailing understanding of fundamental forces encompassed only electromagnetism and gravity. The electromagnetic force, mediated by photons, governs interactions between charged particles, while gravity, described by Newton's law of universal gravitation and later Einstein's general relativity, acts between masses. However, neither of these forces could adequately explain the observed stability of atomic nuclei. Electromagnetism would cause protons to fly apart, and gravity is far too feeble to counteract this repulsion at nuclear distances. The genesis of Yukawa's theory lies in a critical analogy with quantum electrodynamics, or CAD. In CAD, the electromagnetic force arises from the exchange of photons. Yukawa reasoned that if a force could be mediated through the exchange of a particle, then perhaps the strong nuclear force, as it came to be known, operates via a similar mechanism. However, there was a crucial difference. The electromagnetic force has infinite range, a consequence of the photon being massless. The strong nuclear force, conversely, acts only over extremely short distances, on the order of 1 to a few femtometers, or 10 to the minus 15 meters. Yukawa ingeniously connected this short range with the mass of the hypothetical mediating particle. Yukawa postulated that the strong nuclear force originates from the exchange of a new particle, one possessing mass. Unlike the photon, he derived a relationship between the range of the force and the mass of this particle, now known as the meson, using the Heisenberg uncertainty principle, which relates uncertainty in energy to uncertainty in time. He estimated the mass of the meson to be approximately 200 times the mass of the electron. This mass falls between the mass of the electron and Earth of the proton, hence the name meson, meaning middle. A mathematical formalism, presented in Yukawa's 1935 paper, involves a potential energy function that describes the interaction between nucleons, protons, and neutrons. This potential, known as the Yukawa potential, has the form of a negative constant times a radial exponential divided by the distance. Specifically, it is minus g squared, where g represents the coupling constant characterizing the strength of the interaction, multiplied by e to the power of minus mu r, where mu is the mass of the meson times c, the speed of light, divided by h bar, the reduced Planck constant, all divided by r, the distance between the nucleons. The exponential term dictates the short-range nature of the force. As the distance r increases, the exponential term rapidly approaches zero, causing the potential to vanish. The parameter mu, inversely proportional to the range of the force, determines the rate of decay of the potential. The immediate impact of Yukawa's theory was considerable, though its initial reception proved cautious. Physicists recognized the elegance and potential of the idea, but direct experimental verification remained elusive. The predicted meson had yet to be observed. One must appreciate that in 1935, particle physics was in its infancy. Experimental techniques were rudimentary compared to those available today. The search for a new particle with a predicted mass required significant advancements in detector technology and high-energy particle accelerators. A crucial development arrived in 1937, when Carl Anderson and Seth Nerdemeyer discovered a new particle in cosmic ray showers. Initially, this particle, dubbed the muon, was hailed as Yukawa's meson. Its mass closely matched Yukawa's prediction. However, subsequent experiments revealed a significant discrepancy. The muon interacted far too weakly with matter to mediate the strong nuclear force. The muon, it turned out, belongs to the family of leptons, particles which do experience the strong force and interact through the weak force. The discovery of the muon, although initially misleading, spurred further research into cosmic rays and particle interactions. The true Yukawa meson, now known as the pion, remained hidden until 1947. Cecil Powell, Cesar Lattes, and Giuseppe Occhialini, using photographic emulsions exposed to cosmic rays at high altitudes, identified a particle that interacted strongly with atomic nuclei and possessed the predicted mass. This discovery provided definitive confirmation of Yukawa's theory and earned him the Nobel Prize in Physics in 1949. It is perhaps mildly amusing that the initial candidate, the muon, proved to be a red herring, while the actual messenger of the strong force awaited detection through improved experimental techniques, a situation that likely caused some initial frustration Within the physics community, Yukawa's Meson theory also provided a conceptual framework for understanding other nuclear phenomena. The theory explained the saturation of nuclear forces, the observation that each nucleon interacts with only a limited number of neighboring nucleons. This saturation arises from the short-range nature of the meson exchange. It also illuminated the approximate equality of the forces between proton-proton, proton-neutron, and neutron-neutron pairs, a concept known as charge independence. The development of Yukawa's theory had a profound influence on the course of particle physics. It marked the beginning of a new era in which fundamental forces are understood as arising from the exchange of particles. This concept, known as gauge theory, forms the cornerstone of the Standard Model of particle physics, the most successful theory to date describing the fundamental constituents of matter and their interactions. The Standard Model incorporates the electromagnetic force mediated by photons, the weak force mediated by W and Z bosons, and the strong force mediated by gluons, all of which are examples of exchange particles. Moreover, Yukawa's work paved the way for the discovery of a multitude of other mesons and hadrons, particles composed of quarks bound together by the strong force. The pion, initially envisioned as the sole mediator of the strong force, turned out to be just one member of a large family of mesons, each with its own unique properties and interactions. These discoveries led to a deeper understanding of the structure of hadrons and the dynamics of the strong force. The evolution of the theory of strong interactions did witness some interesting twists. While Yukawa's original theory proposed a scalar meson, the pion is actually a pseudo-scalar meson, possessing odd intrinsic parity. Parity, a quantum number that describes the behavior of a particle's wave function under spatial inversion, plays a crucial role in determining the allowed interactions. The pseudoscalar nature of the pion necessitates a slightly different form of the interaction, involving the derivative of the Pilon field. Furthermore, the simple picture of meson exchange as the sole mechanism for the strong force proved to be an oversimplification. At very short distances, the underlying quark-gluon structure of hadrons becomes manifest. Quantum cryptodynamics, or QCD, the theory of quarks and gluons, provides a more fundamental description of the strong force of these scales. Meson exchange remains a useful approximation at larger distances, but QCDs require for accurate calculations at high energies. Despite these refinements, Yukawa's meson theory retains its enduring significance. It represents a bold and ingenious attempt to explain a fundamental force of nature, an endeavour that required a profound understanding of both quantum, mechanics and nuclear physics. The theory introduced the concept of exchange particles, a cornerstone of modern particle physics. It stimulated a vast amount of experimental and theoretical research that continues to this. Regarding critiques, several challenges and revisions emerged following the postulation of Yukawa's theory. The initial experimental ambiguity surrounding the muon, erroneously identified as the meson, highlights the difficulties in early particle detection and identification. This confusion prompted a deeper examination of particle properties and interaction mechanisms. Another critique involved the strength of the meson nucleon coupling constant. Earlier estimates suggested a value that appeared too large for perturbative calculations, raising concerns about the validity of the theoretical framework. This issue was partially resolved with the development of renormalization techniques in quantum field theory, which allowed for more accurate calculations even with strong coupling constants. Additionally, the realization that the pion is a pseudo-scalar meson, the original formulation involving a scalar meson, raised questions that required modification of the interaction Lagrange. A further development centered on the limited applicability of the meson exchange model at very short distances, as experimental probes attained higher energies, revealing the internal structure of nucleons. The quark-gluon picture of QCD became increasingly important. This led to a more nuanced understanding of the strong force, where meson exchange serves as an effective theory at lower energies, while QCD governs the interactions at shorter distances. The reception of Yukawa's theory within the global physics community was initially mixed. While many physicists recognized its elegance and potential, the lack of direct experimental confirmation and the theoretical challenges associated with strong interactions led to a period of cautious optimism. The subsequent discovery of the pion and the development of relativistic quantum field theory solidified the theory's standing and cemented Yukawa's place in the history of physics. Direct influences on Yukawa's work undeniably include quantum electrodynamics and the pioneering work of physicists such as Werner, Heisenberg, and Paul Dirac. The concept of force mediation through particle exchange, as demonstrated in QED, served as a crucial inspiration for Yukawa's proposal. Heisenberg's uncertainty principle provided the essential link between the range of the force and the mass of the mediating particle. Dirac's relativistic wave equation provided a mathematical framework for describing the behavior of particles at high energies. Beyond these direct influences, The broader intellectual climate of the 1930s, characterized by rapid advancements in quantum mechanics and nuclear physics, played a significant role in shaping Yukawa's thinking. The experimental discoveries of the neutron by James Chadwick and the positron by Carl Anderson provided crucial pieces of the puzzle, fueling the quest to understand the fundamental structure of matter. As for the direct influence of Yukawa's work on others, the discovery of the pion by Cecil Powell, Cesar Lattes, and Giuseppe Occhialini demonstrated a definitive confirmation of Yukawa's prediction and prompted a surge of research into meson physics. The development of quantum field theory, particularly the work of Richard Feynman, Julian Schwinger, and cynic Hiro Tominaga, built upon Yukawa's concept of particle exchange to create a comprehensive framework for describing fundamental interactions. The subsequent formulation of the standard model of particle physics, which incorporates the electroweak and strong forces, owes a significant debt to Yukawa's pioneering work. The story of Hideki Yukawa's meson theory speaks to the power of theoretical insight, coupled with experimental verification, in advancing our understanding of the universe. Yukawa's bold hypothesis, born from analogy and guided by fundamental principles, unlocked a new chapter in the history of physics. Even with its subsequent refinements and the emergence of QCD, the meson theory remains a testament to the enduring legacy of a brilliant mind. The theory stands as a pivotal contribution to our comprehension of the forces shaping the cosmos, a contribution that continues to inspire physicists today.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.